Let's try to work on the answers together. So the first 4 questions are just some supplementary exercise for the case for some mathematical techniques related to differentiation. And no worries, because for this course, we don't need to refer to the techniques of differentiation, and we only take the slope into consideration instead of the actual mathematical techniques. But still, let's try to work on this. First of all, we need to take the first derivative on the area of A with respect to the radius. We can go over the basics of the differentiation. We just put down A equals to pi r squared. The answers will be shared with you after we finish all the questions. So please feel free, just need to follow what we discussed. This is what we have by definition if we don't skip any steps. What we are going to move forward is that we know the only variable will be the radius r. For all the rest of the stuff, they're just referring to constant. So pi, this is constant so that we can take away from the derivative. And now we have r squared left behind the derivative. Taking the first derivative of r squared simply, this is 2r. You can refer to the formula in the lecture notes, where this is rule number 2, that this is the derivative of r to the power n times. Or we rearrange the equations, we have 2 pi r. Part B follows the answers of part A on the determination of the geometric quantity. So what is 2 pi r? 2 pi times radius. No, for diameter, this is 2r. How about 2 pi r? 圆周. Okay. 圆周, this is the circumference. Of a circle. Simply, question 1 is referring to 2D. We are considering a circle. And now in question 2, we move to a 3D, that is a sphere. The sphere, it is given that the volume is 4 pi times pi r, the cubic of r. The first derivative is simply similar to what we have in the first question. Just put down v in terms of the cubic of r. Again, only r is the variable, so we just take the constant out of the first derivative. Constant remains a constant for all the steps. The first derivative of the cubic of r is 3r squared. If we simplify the fractions, we have 4 pi r squared. As you can observe, after taking the first derivative, we know the power order of the radius dropped from 3 to 2. Originally, volume, this is depending on the cubic of R. This is our power order of 3. After the first derivative, the power order decreases by 1. And now the first derivative depends on the square of R. That is power order of 2. So what is the geometric quantity of 4 pi R squared? Any idea? Total surface area, yes. This is the total surface area of the sphere. As a supplement note, if you feel not comfortable to differentiation, simply you can treat differentiation as a delta, which is the change on the numerator over the change of the denominator, given that you consider the change is within a tiny step size. For example, if you consider the quantity dx by dt, in general, t is time. If you consider, if you consider this is very small and we just say tends to 0, all the things can be written as delta x over delta t, which means we have x2 minus x1 divided by t2 over t1. This is exactly what we have for the consideration of the slope. Given that we consider a small change in the time, we just consider a slope between 2 points. For question 3, we come up to the consideration of a physical quantity C. Simply, this is some variable C that has constant value for all time t. We need to sketch the graph C against time. C against time means C is the y-axis and time will be the x-axis. This is how we describe the 2D graph. I'll just put down what we have. We have C on x-axis and we have time on the x-axis. And now what we know is that the C equals to A at all times. That is C equals to A for all time. It means for all. So that we just draw a horizontal line and say this is equal to A. A could be some non-zero value so that you can draw on the upper part of the coordinate system or the lower part. We don't know whether it is positive or negative. Since we know C equals to a constant, if we take the first derivative on C, simply this is equal to 0. This aligns to what we have for the understanding on the graph. Taking the first derivative on this graph, which means we are considering the slope. This aligns with our understanding on a horizontal line will have a slope of 0. This is what we have for part B. Just cover it here. This is part B. For question 4, we are given a quadratic formula depending on the second order of the t. We don't know whether time whether t is time. Simply just check. We have two variables, x and t. And now x will be the dependent variable because we put it on one side and the other variables on the other side. So x is dependent variable and t will be independent variable. Now we consider a first derivative, the x by dt. Indeed, the differentiation will have a property that the summations of taking the derivative on the summation of several components equals to the differentiation of the individual components. So that we have the summation of 3 derivatives on A, on BT, and on CT squared. For the first part, A is constant, so that this is simply 0. For the second part, this is the first order having the constant B and variable T. Of course, we may take B out of the derivative because this is a constant. On the third part, we take C out of the derivative. Of course, if you are comfortable, feel free to skip these steps. But this is how we could better check, verify our answers if we don't skip any step. We have 0 plus b dt by dt simply this is exactly equals to 1 plus c. The first derivative of t squared, this is 2t. And now we have b plus 2ct. Originally, x depends on the highest power order of t. This is equal to 2. And now, after the first derivative, we know the power order drops by 1, so that it depends up to t only with a power order 1. And now we come to the major contents of mechanics from question 5. Best to what we have for mechanics. Let's start with the basics. Let's consider a graph. The graph shows this is a VT graph. The VT graph shows the changes of the velocity when the ball throws upwards, and when it throws upward and reaches a maximum point, the ball drops. First of all, we assume vertically upwards as positive. This is very important. Remember that just all of the questions are just defined the positive direction. And now what we have is we are considering a 1D motion. We only consider vertical direction. This is 1D. We are given the information of 2 points at t equals to 0 seconds and at t equals to 4 seconds. We are given the exact information of 2 points. In part A, it is about when does the ball reaches the maximum height. Indeed, what we know is that when we consider the motion of the ball, we are floating up a ball. The ball should goes up, and at some point under the influence of the gravity, so it must drop after some period of time. When it goes up and reaches the maximum point, it will drop. At this point, we consider this is the maximum height. When it goes up, we know the velocity should be in positive direction because we just assume vertically upward as positive. So when we throw up the ball, basically it is having positive velocity. And after some moment it drops, it is moving downward, so it will have negative velocity. Between the movement of the upward and downward position at maximum height, it should have velocity equal to 0. When v equals to 0, what we know is that this is the special stage of momentarily at rest. It means that the velocity changes its direction. This is the moment where the velocity changes its direction. From positive to negative at the intersection point, we should have 0 for the velocity. In part B, we need to find out the magnitude and also the direction of the acceleration. We are given a graph. This is VT graph. We know taking the first derivative on the VT graph, we get the acceleration. Or we can consider the slope in the VT graph. To find out the slope, we can refer to the graph, and we only need to select 2 points. Indeed, we have the information of 3 points. The first 2 points are given in the question, so we have the information of 2 points. We can make use of this to find out the slope. Or we can make use of the understanding of the point at maximum height. This is what we know. V equals to 0 at time equals to t. Time equals to 2. T equals to 2 seconds. This is 0 meter per second. So we have 3 points. We can make use of any 2 points to find out the slope. Let's refer to what we have from the questions. The slope equals to the change of the velocity. Change means final minus initial velocity. This is what we refer to delta V. Slope, you can consider this is differentiation dV or delta V. For the denominator, this is referring to time axis, so that we have final time minus initial time. In this graph, we consider final point is t equals to 4 seconds. This is what we have. And we have minus 9.8 meter per square second. If you forget about the what unit will be the final answers, you may refer to what we have from the formula. And then when it comes to the slope, in the numerator, we have the change of the velocity. The velocity is with units of meter per second. When it comes to units, this is meter per second in the numerator over the change of the time. Time is in second, so that we can deduce that the final unit of our answer, which is the acceleration, is meter per square second. So this is a very good alternative to find out the unit of your answer. In case if you do not remember the SI unit of the physical quantity, you just go to your formula and you derive your own unit. In this answer, it already tells us the magnitude. Magnitude means just take absolute value. This is 9.8. And the direction, we have positive and negative. Negative means this is pointing downward, because we assume vertically upwards as positive, so that downward will be negative. This is what you can express, or you can say we have absolute A equals to 9.8. And also this is in downward direction. We just write down minus 9.8. This will be the same, because positive or negative will help us to take care of the direction, given that we define positive y direction. In part C, does the value of the acceleration depend on whether the ball is ascending or descending? Let's take a look, try to break this question into two parts. First of all, let's check the information. The ball is ascending. When ball is ascending, ascending means going up, 上升. So that when ball is ascending, what we know is that it must have, it must follow positive velocity. For the case of the ball is in descending, so this is dropping downwards. it should follow negative velocity. If we compare these two scenarios, whether the ball is going up or going down, what we can see from this graph, the VT graph, is that the slope remains constant. When slope in the VT graph remains constant, what we know is that the acceleration is constant. This is from this information can be drawn from this graph, or this is based on part B. From part B, we only have the information of acceleration equals to -9.8. This exactly tells us the acceleration is constant. If the acceleration is constant, for sure this is independent to these two scenarios. Therefore, the answer simply this is it does not depend on the scenario. Is it okay? If you have any questions, just feel free to interrupt me. In question 6, we try to consider the 1D motion. Again, this is a 1D motion. The particle is moving along the x-axis with constant acceleration. We are given the information of, again, 2 points. At time t equals to 0 and at time t equals to 10 seconds. First of all, we try to consider a problem using graphical method, where we try to draw the VT graph. Since we're going to draw the VT graph, we need x-axis and y-axis. For y-axis, this is velocity, and for x-axis, this is t. Bear in mind that for both the axes, put down the unit. This is very important. Just don't miss the unit. What's more is that just define the 0 so that we'll have a better understanding on the definition of the graph. This is what we have. We just put down all the basic stuff. And now we just refer to the information on the question, where it gives us the information of 2 points at time t equals to 0 seconds. This is -10 when time t equals to 0 seconds. At some point, we are having 10 seconds. The particle reaches the velocity of 40. What we know is that the particle is moving with constant acceleration. Which means for VT graph, we have constant slope. For constant slope, simply, we know constant slope means the slope remains same throughout the curve, so that we just line up these 2 points. with a straight line. Keep in mind that this is a straight line. A straight line means this is having a constant slope. Since it follows a constant slope, so that the increment of the velocity, because the velocity goes up from -10 up to 40, so this is an increment of the velocity. This is following a fixed ratio, and we should deduce that this is reaching zero velocity when time t equals to 2. This is what we can deduce. Indeed, you can find out the acceleration easily, because you can follow the formula A equals to V minus U divided by T. This is how you can find out acceleration. With acceleration, we understand all of the steps for the linear motion. In part B, it asks about when is the particle momentarily advanced. We just mentioned in question 5 about the concept of momentary advance, which means the object starts changing its direction. This is momentary advance. We know when the object changes its direction when it reaches the velocity of 0 meter per second, so that at time t equals to 2 seconds, it goes to the state of the momentary advance. So then in part B, we know this is t equals to 2 seconds. Because the direction of V changes. In this case, from negative to positive. In question 5, the velocity changes from positive to negative. In question 6, we have an example of the changes of direction from negative to positive, which implies that as long as the direction of velocity changes, we can say this is having the state of momentarily advanced. In question C, when does the particle traveling in the direction of increasing x? Indeed, we can refer to the direction of the velocity. When will be the increasing the direction of increasing velocity? If we go back to what we have from part A, we know this is what we have. At t equals to 2 seconds, it is with e equals to 0. When t larger than 2 seconds, we know we have positive velocity. so that the answer will be t larger than 2 seconds. Again, in question 7, we consider, we start from a graph. We consider a VT graph between t equals to 0 to and 4 seconds. First of all, we need to determine when the particle reaches 0 acceleration. From the VT graph, we know if we find out the slope, we know the acceleration. We need to consider a slope of VT graph equals to 0. How can we find out the instant when the slope equals to 0? 0 slope means this is a horizontal line. Somewhat from this graph, we know horizontal line will be the point around 2 seconds. If we write down 1.9, 2.1, close to 2, this is all perfect. Unless we enlarge the graph. This is around 2 seconds. In part B, we need to determine the maximum value for the acceleration, which means we are considering the steepest slope, which is the large value. Either this is positive or negative. Both could be fine. I guess you should we're going to search around around 1 second. Around 1 second, you just take any 2 points into consideration. Then you can find out the maximum value for the acceleration. For example, I take 2 points at t equals to 0.9 and also t equals to 1.3. At this top, at these 2 points, I get v equals to 40 and v equals to 80 meters per second respectively. I guess you'll find a similar readings by observing the figure. Find out the acceleration. We consider v2 minus v1 divided by t2 minus t1. Since our time keeps increasing, what we know is that we have t1 to be 0.9 and t2 to be 1.3. So v1 40, v2 80. we get the value of 100 meter per square second. In question 8, if we consider a position of a particle related to time t by the equation x equals to et minus ft cubic t. First of all, we need to find out the first derivative. Just put down. We have a differentiation of two parts. Again, we just take out all the constant. They are independent to the differentiation. Both E and F are constants. dt by dt, this is 1 for the differentiation of a cubic of f. This is 3f squared. Sorry, this is t. Sorry for my typo. This is t. This is expected. Originally, it depends on the highest order of 3 for t. After the first derivative, the power order dropped by 1. So at most, we are having power order of 2 for the variable t. If you take a look into a question, it is referring to a position. Position is indeed referring to a reference point. Therefore, we just mentioned in the lecture that position has an alternative naming called displacement. So that you can replace x with x in the equations. In part B, we are given the values for the constants, and if we consider the particle, which is the momentary effects, which means v equals to 0. We are given the information of the displacements versus time. If we take a look into the first derivative on the displacement versus time, this is exactly equals to the velocity. What we know is that v equals to dx by dt, or you can say ds by dt. The displacement time graph. A displacement time graph, the slope equals to the velocity. This is what we have from this expression. Since we need to consider the state when the particle is momentary at rest, so we just put down dx by dt equals to 0. so that we have e minus 3ft squared goes to 0. The answer in A goes to 0. We have E to be 2.7 and F to be 0.1. And now we can find out the information of T. T equals to 3 seconds or T equals to minus 3 seconds. Keep in mind that we have two solutions because this is a second order equation depending on power order of 2 for T. In general, we reject the answers that is behind. Because what we are considering is the movement of the particle. When we start, the consideration time should be from 0 seconds. This is the minimal value of T. So that's why very often we try to reject the oldest value, particularly if time is negative. Let's take a short break in case if you have not yet finished the rest of the questions, just do it now. And we'll cover the rest of the questions after the break. Let's move forward. We go to question 9. In question 9, we consider again a 1D motion on the x-axis, where we get a constant acceleration and the particles is traveling with initial velocity of -10 with initial position. Keep in mind that we have a little bit tricky assumption is the initial position. In general, very often we consider the reference point, which is 0. But now the initial position comes to 10 meters. At some point, if you consider the displacement, then you need to take the reference point at 10 meters. The reference point is 10 meters because this is the initial location. Remember, we have derived 4 equations for the motion, where in some equations they depend on the displacement. But those displacement, please make sure that it comes from the initial position of 10 meters. Let's start with part 8. When will the particle momentarily advance? What we know is that the initial velocity is negative, and it is accelerating with positive acceleration. So the velocity will be increased. Therefore, the initial velocity, which is negative, will increase and reaches 0 meters per second at some point. And after that, it will go to positive velocity. Therefore, we need to find out V. To find V, what we are given is that we have U, we have A, and also we have the information. Let me check. Sorry, we are not finding V. We are finding T. Sorry, because it says when. So we find T. We have U. We have A, and also we have V. We have U, V, and A. We need to find out T. Then we can make use of one of the equations. This is V equals to U plus AT. Since this is moving along x-axis, in some case, we can put down the subscript. The subscript just specifies we are considering the motion in x direction. The V will be the final velocity, where this is the situation where the particle is momentarily advanced. So Vx goes to 0. This is the case when it is momentarily advanced. For U, this is initial velocity -10 with A, this is constant acceleration, +2. And time t will be the unknown. And now we know time t equals to 5 seconds. So after 5 seconds, the particle increases its velocity and goes to velocity of 0. After that, it will have a positive velocity. In part B, it says that where does the particle when it comes to momentarily advance? That is, we need to find out the position when the particle is at t equals to 5 seconds. To find out the location, we need to find the displacement. Therefore, we're going to find the displacement s. Find out the displacement, we can only use the unique equation s equals to ut plus half a t squared. Again, we can put down the subscript x to denote this is in x direction. The displacement is unknown. For u, simply this is minus 10. What is time t? Time t is simply what we have from part A, dx equals to 5. This is from A. Now we just put down t equals to 5. We have half to 5 squared. And now we get the displacement. This is minus 25. The unit is meter. Bear in mind that we have not yet obtained the final answer. This is the displacement of the movement of the particle from the initial position. Therefore, we need to take care about the initial position, which is the reference point. Because the initial position, we have x0, this is 10 meters. Therefore, the actual position of the particle which is just the initial position add up with the displacement. This is 10 minus 25, in which the actual position will be minus 15. In which it is moving in a reverse direction. In question 10, we consider we are dropping a stone at some point and reaches the bottom of the well. This is what we have if we drop the stone which falls vertically downwards. It takes 4 seconds to reach the bottom. We need to find out the depth of the well, which is the distance between the initial and final position of the stones. Before we make use of the equation, what we have to do is to define the positive direction. Since the motion of the stone is vertically downwards, for convenience, simply we just take vertically downwards as positive. We just follow the direction of the movement. To find out the things are related to the distance or the displacement, both are the same, given that this is a one-dimensional motion, so that distance equals to displacement in one-dimensional consideration. And here, just make use of the unique formula. This is S equals to ut plus at squared. Since this is in a vertical direction, or perhaps you can specify this is in y direction, we just put down the subscript y. The displacement will be the unknown. We need to find out the displacement as the depth of the well. What will be the initial velocity? Any idea? 0, because this is from rest. That implies the initial velocity equals to 0 because this is from rest. 0 for time t, this is 4 because it takes 4 seconds to reach the bottom of the well. We have half at squared. What is 8? 9.8 or 10. A equals to the acceleration due to gravity, or you can say the gravitational force. So I should put 10 for simplicity. So AY simply, you can say this is equal to GY, this is equal to 10, or we can use 9.8. For easiest calculation, you may use 10. 10 or 9.8 will be fine. And now we get a displacement of 80 meters, so that we know the depth of the well is 80 meters. Either we put down the written description to conclude the depth of the well, or we just draw it on the graph and say this is SY. So both will be the same. Either we draw a simple graph to specify our definition of the variables, or we just conclude by some written descriptions. In question 11, here comes to the discussion of the Newton's law of universal gravitation, where there will be interaction between two objects. For example, between Moon and Earth, the Earth and ourselves, and we have many more examples for the interaction due to the Newton's law of universal gravitation. Indeed, the interaction follows Newton's third law, which is action and reaction pair, same magnitude but opposite direction. What we are going to do is to find out the magnitude of the force on the Earth by Moon. We can refer to the formula. This is the force equals to G the product of the mass of the two objects divided by the r squared. R is the distance between the center of the two objects. For capital G, this is the constant that you can refer to the value on the list of the equations. So feel free to use any of the formulas and also the values for the constants in the list of equations. So that I shared with you last week. This is for capital G, this is 6.67 times 10 to the power minus 11. This is G. For M1, M2, they're just the mass of the Earth and the mass of the Moon, respectively, which is given in the question. Let's cover the three parameters in the numerator. In the denominator, this is the radius. Of the, this is not the radius, this is the distance between the center of the Moon and the center of the Earth. Given that the center of the Moon and the center of the Earth is separated by 60 times of the Earth radius. We have the 60 times of the radius of the Earth. So this is 60 times 6.37 times 10 to the power 6. Keep in mind that put down the square. Force is huge. This is 2 times 10 to the power 20 in Newton. Again, in case if you forget about the unit of the force, you can derive the unit based on the equations. If you take a look into the formula, the unit in the numerator, G is constant. Forget about the unit. So we have kg times kg. For numerator, for denominator, the distance is following a unit of meter. So we have meter squared. Indeed, we can derive an alternative unit for this. This is just for a case that you forget about the SI unit. But for sure, Newton will be more common as the unit of the force. In question 12, we have an example to recap what we have for a consideration of the in the lecture notes. We say the man gains weight and lose weight easily when he's standing on the lift, where the lift is accelerating upwards or downwards. So let's consider a very similar case. Given that in part A, the lift is stationary. If the lift is stationary, this is at rest, which means there will be no acceleration. Keep in mind that lift goes upward or downward, so we are considering the y direction. We can consider the Newton's second law. This is Newton's second law. For Newton's second law, the net force acting on the body goes to the product of ma. This is 0 if the lift is at rest. Since we need to consider the information of net force, we need to define all the forces acting on the woman. In this case, we need to draw the free body diagram. The free body diagram specifies all the forces acting on the body. So this is 60 kg. There will be two forces acting on the woman in y direction, or you can say vertical direction. The first one for sure, this is the weight equals to mg. And also it has the force, this is the normal reaction. For a free body diagram, we know there are two forces acting on the body, and these two forces contribute to the net force. Before that, we need to define the positive y direction. We can define upward or downward as a positive direction. Just say vertically upward as positive. If we say vertically upward as positive, the net force is now defined as R minus W. Of course, it goes to 0. So the normal reaction becomes the weight. This is equal to mg. The mass is 60 kg. G is 10. This is 600 Newton. Keep in mind that we only need to consider the magnitude in this question. We already specified the magnitude, so don't care about whether this is a positive or negative value. As long as whether the things are positive or negative, this will be included by the definition of the positive y-axis, which is pointing vertically upwards. How about if the lift is accelerating upwards at 2 meters per square second? Now we define AY equals to positive 2 meters per square second. Again, we can refer to the Newton's second law with the same formula. That is, the net force in y direction equals to ma. Again, net force, we refer to the same definition for the using the free body diagram, where there are only two forces. We have R minus W exactly equals to what we have in part A. This is our MAY. What we need to do is to determine the normal reaction. So we have the weight plus MAY as the normal reaction. The weight is mg with MAY. Mass is 60, G is 10. The same part, mass 60 and A goes to 2. Normal reaction is larger than the weight, where virtually the movement gains weight as a result of the lift is accelerating upwards. In part C, this is just the reverse case of part B. If acceleration of the lift is pointing downwards with -2 meter per square second. Again, by Newton's second law, just recap what we have in part A and part B. I just go through quickly. Again, R equals to W plus MAY. And this is mg plus MAY. But now there will be a little bit different because the acceleration is now -2. So that's the normal reaction goes below the weight. This is 480 Newton. So virtually the woman loses weight when the lift is accelerating downwards. Let's move to the last question of tutorial 1. It says that we are considering a car is moving a motorway at 27 meters per second. Then the car is going to stop as a result of the braking is applied. And it says the tires slide over the tarmac surface of the road. We need to use the formula given in the lecture notes, given that the sliding, the coefficient of sliding friction is 0.7. And to find out the value of G to estimate the magnitude of the car's acceleration. What we are going to do is to find out the acceleration of the car. Let's try to better understand the scenario by drawing the three-body diagrams. With the three-body diagrams, we have better understanding on the forces that affect the car. Let's consider we have a car. For sure, it is having the weight. This is pointing vertically downward. Of course, it is standing on the road and experiencing the normal reaction. This is what we have. We have two forces on y direction. If the car is moving towards the right, this is just for assumption, either it is moving towards the left or right. If it is moving towards the right, we can define the car is experiencing the friction. This is in opposite direction of the movement. The friction is in opposite direction of the movement. The friction, we can denote it as this is a force that is with subscript small letter f. To denote this force is referring to friction. Since we have forces on x and y direction, this is a 2D scenario. In 2D scenario, we need to define both the positive x and positive y direction. For example, we can define vertically upward as y. Let's try a little bit different. If we define horizontally towards the left as x, let's try to define in an opposite way to see whether we can manage the formulations with different definition of the positive directions. In 2D problems, we try to break down the 2D problem into two pieces. One is in x direction and one is in y direction. Because in x and y direction, things are perpendicular to each other, so that these two subproblems are independent to each other in the formulations. If we consider the x direction contributes to the movement, where we can apply the Newton's second law. In Newton's second law, we only know one information: the net force equals to ma. In this question, we need to find out the acceleration A. What will be the net force? In x direction, from the free body diagram, we only have one force acting on the car. That is the friction. The friction is exactly equal to net force. Just say this is equation 1 based on the consideration in x direction. Let's check the formulation in y direction. In y direction, again, we can consider Newton's second law. Now, Newton's second law will be specified by subscript y. This is in y direction. So again, net force in y direction equals to the product of mass times acceleration in y direction. Indeed, what we know is that the net force contributed by two forces, the normal reaction R and the weight W. Since we define vertically upward as positive, so that the net force R minus W on right-hand side, simply we can simplify this equation, because when a car is moving horizontally, basically it should remain on the road or on the ground. Otherwise, the car may fly over the air. So in this case, we must know the acceleration in y direction should be 0. The car stays on the road. Just simplify this equation by put down R minus W equals to 0 or R equals to W. This is equation 2. Can we correlate, have a better correlation between equation 1 or 2? Of course, yes. If we try to further expand the friction as the product of the coefficient of the sliding friction with the normal reaction. In this case, we can put equation 2 into equation 1 because the friction depends on the normal reaction R. Now we're going to substitute equation 2 into 1. Just put 2 into 1. Since R equals to W, the friction comes to exactly the coefficient of sliding friction times the weight equals to MA. The weight equals to mg. On both sides of the equation, simply we just eliminate m. Now this is what we have. The acceleration depends on the coefficient of the sliding friction and the gravitational constant. Keep in mind that we need to find out the acceleration on the cars that is a subscript x. Make sure the dependent variable should be put down on the left-hand side of the equations. Make sure that this is not correct. The variable should be put down on the left-hand side of the equation. So that's why we just move A from right to the left. What we can observe is that the acceleration is positive based on what we have defined before. We say towards the left is positive x direction, so that the car is indeed accelerating with in positive x direction. This is exactly what we have to explain when the car is moving towards the right. The movement is let me check. The movement is towards the right. The friction is applied toward in opposite direction. And what we are finding is that the acceleration on the car is towards the left. This is true because we are applying the brake to stop the car. That's why the acceleration should follow the same direction of the friction. This is towards opposite direction of the movement. Is it okay for tutorial 1? In general, tutorial will cover more questions. There is more general questions and more simple questions on the topic. And for supplementary exercise, which is the questions from past quiz or exam papers, that may be a bit more difficult and will be a lengthy questions in some sense. Let's move to supplementary exercise, and perhaps we can finish 1 or 2 questions. In the meantime, I will distribute the answers for In question one, suppose we are dropping two balls, ball A and ball B at some point. Both of them are initially at rest. So that UA equals to 0 and UB equals to 0. They are at different heights from the ground, HA and HB. And it says that ball A drops first and ball B drops 1 second after. Both of the balls reach the ground at the same time. And that is 6 seconds after ball A is dropped. We need to find out the difference of the height. That is HA minus HB, given that HA is larger than HB. To find out HA minus HB, simply we just find out the displacement of both balls reaching the ground. Let's try to consider ball A first, because the drop of the ball should work independently. So we consider A only. For simplicity, the positive direction just follows the movement of the ball. That is, vertically downward is positive. We need to find out the height. The height simply referring to the displacement of the ball at initial position, which is the ground. Find out the displacement, the only equation that we can use will be S equals to UT plus half AT squared. If the symbols are tailor-made to our interest, S simply equals to H subscript A. For U, this is referring to ball A. For T, we just put down things. This is our TA. We need to find out HA equals to, initially the ball is at rest, so we put down 0. How about time T? We know time T for A. This is 6 seconds. For the acceleration acting on A, simply this is acceleration due to gravity. Exactly, this is equals to G equals to 10. We get the height of the ball. This is 180 meters. This is the information for ball A. For ball B, we apply a similar formula because we are interested in the height, which is the displacement of ball B. Again, we follow the same equation. And now we just specify the symbols. This is for ball B. Again, ball B is initially at rest. How about the time for ball B? Given that we drop ball A first and we drop ball B 1 second after, therefore, the time taken for ball B to reach the ground is 6 minus 1. This is 5 seconds. The height is just 125 meters. With the information of the heights for ball A and ball B, we can find out HA minus HB. This is 180 minus 125. This is 55 meters. We say HA minus HB, or we can say subtract HB from HA. In case this is not that easy to understand, you can say from HA subtract HB. Either you say HA minus HB, or you just write down subtract HB from HA, or from HA subtract HB. This is how we describe the subtraction between two things. In part B, we need to find out the speed of ball A when it hits the ground. Speed is, you can say this is velocity, because we are having a 1D motion. This is our velocity in 1D. We can apply the formula to find out the final velocity or final speed. V equals to U plus AT. Since this is for ball A, just put down the appropriate subscript. Initially arrest means U equals to 0. The acceleration is purely 10 due to acceleration due to gravity. T is just 6. The speed of velocity is 60 meters per second. Perhaps time is up for this class. I just leave the remaining questions to next week. In case if you have a problem, just let me know, and feel free to send me a message during weekend in case if you have any difficulty during revision. So see you next week. Thank you.